Section 2-5 is on postulates and paragraph proofs. Now, a postulate is a statement that is accepted to be true without proof. It's usually something so simple, so basic that we don't even bother to prove it. And since points, lines, and planes are undefined terms, we have several postulates about them. Now, the numbering on this is kind of random. It's just based on the textbook, but you're welcome to use the numbers. 2.1. Through any 2 points, there is exactly one line. 2.2. Through any 3 non-collinear points, there is exactly one plane. Now 2.3 and 2.4 are kind of the reverse of the first two. A line contains at least 2 points, and a plane contains at least 3 non-collinear points. 2.5. If 2 points lie in a plane, then the entire line containing those points lies in the plane. 2.6. If 2 lines intersect, then their intersection is exactly 1 point. And 2.7. If 2 planes intersect, then their intersection is a line. So here's an example. Determine whether each statement is always, sometimes, or never true, and then explain. If plane R contains line EF and point G lies on line EF, then plane R contains point G. Let's draw a picture of this to make it a little more clear. So here's plane R, and I'll label it. Here is line EF that lies in plane R, and then plane R, and point G lies on line EF also. So then the question is, does plane R also contain point G? And yes, it does. This is a true statement. Because according to postulate 2.5, if 2 points lie in a plane, then the entire line containing those points also lies in the plane. So since line EF is in the plane and point G is on the line, point G lies in the plane. Example number 2. 4 points are non-collinear. Well, this is sometimes true. Because I could have a line that contains 4 points, A, B, C, and D, and those would be collinear. So points A, B, C, and D are collinear, but any 4 random points, let's put point E out here, that is not collinear with, for example, A, B, and C. But points A, B, C, and E are non-collinear. So sometimes it's true and sometimes it's not. A proof. We've talked about these a little bit in class already. A proof is a logical argument which uses deductive reasoning, not the inductive reasoning that we talked about at the beginning of this chapter. Each statement that is made is supported by a reason that is accepted to be or has been proven to be true. So every time we say something in the proof, we have to back it up with a definition, a theorem, a postulate, or something that has already been accepted to be true, like a postulate, or proven to be true, like a theorem. And a paragraph proof is just a proof that uses sentences. Let's try one here. Given that point C is between A and B, and segment AC is congruent to segment CB, write a paragraph proof to show that C is the midpoint of AB. The first part of any proof is to write what you're given, and we write the word given and underline it. Then we have to write what we're going to prove. So you're always given certain information that's accepted to be true, and then you have to work your way through the proof to get to what you're supposed to prove. So what is given is that C is between A and B. So that means that A, B, and C all lie on the same line. And it's also given that segment AC is congruent to segment CB. Okay, just took that right out of the example there. And it says write a paragraph proof to show that, and here's what I have to prove, C is the midpoint of AB. Okay. First part of a paragraph proof is to state in a sentence what is given. It is given that C is between A and B, and that AC is congruent to CB. And it might sound a little bit repetitive, but the first step of doing any proof is always to state what is given. Okay? So if, now we're going to build on that. So if AC is congruent to CB, then we know that the length of segment AC is the same as the length of segment BC. And that is by the definition of congruent segments. The definition of congruent segments says that if two segments are congruent, then their lengths are equal. Up here we said AC is congruent to CB, so I can say AC, the length of AC is equal to the length of CB. Okay? Then by the definition of midpoint, if you remember back to chapter 1, the definition of midpoint says that if C is between A and B, and if AC is equal to CB, then C is the midpoint of AB. So, and I've basically gotten to my proof, what I had to prove. So what I had to prove is that C is the midpoint of AB. I state that at the very end, and to get there I use the definition of midpoint. Let's try another example. Given that AE, segment AE is congruent to segment DB, and that C is the midpoint of both AE and DB, then we need to write a paragraph proof to show that AC is equal to BC. So let's draw a picture. So I have segment AE, and I have segment DB, oops, and I know that C is the midpoint of AE, so that means these two are congruent. It also means that C, oops, I forgot to label C. Let's get C in there. And C is also the midpoint of DB. What I have to show is that segment AC is equal to segment BC. Okay, so to start my proof, I'm going to write my given. AE is congruent to DB. And C is the midpoint of AE and of DB. And what I have to prove is that AC equals BC. Now the nice thing about doing a proof is you can always write the given in the proof without having to do a whole lot of thinking. So let's start. So I'm going to state part of what is given. Since C is the midpoint of AC, I'm sorry, not AC, AE, then AC is equal to CE, which is equal to 1/2 of AE by the definition of midpoint. Okay, and since C is also the midpoint of DB, then DC is equal to CB, which is equal to 1/2 of DB, also by definition of midpoint. So what I basically said is, since they told me that C was the midpoint of each of these longer segments, I basically said AC is equal to CE, and DC is equal to BC, but then taking it one step further, if C is the midpoint of AE, then each one of these little smaller segments is 1/2 of the large segment. Okay? Now I want to say it is given that AE is congruent to DB. Remember, that was part of our given. And by the definition of congruent segments, remember, I can say, instead of saying that they're congruent, I can now say that they're equal to each other. AE is, the length of AE is equal to the length of DB. Okay, and taking that little equation and multiplying both sides by 1/2, I get 1/2 of AE equals 1/2 of DB. So I took this statement right here, AE is equal to DB, multiplied both sides by 1/2. Multiplication property says I can do that. Now notice I had, I'll go ahead and underline this, I had a 1/2 AE up here. Oops, I want AE up here. Then I also had a 1/2 AE down here. I have a 1/2 DB right here, and I have a 1/2 DB right here. So by substitution, so instead of 1/2 AE, I could actually write AC, because 1/2 of AE is equal to AC. And 1/2 of DB is the same thing as BC. Or actually I said CB, but it doesn't go either way. And I have proved what I needed to prove. AC is equal to BC.